Thank you so much for joining me today and taking WebAssembly for a spin. I'm Michelle Dhanani. I'm a software engineer and a founding member at Fermyon, where we're building tools and technologies to pioneer the next wave of cloud computing. A little bit about my history. I've spent the last several years helping build and maintain open source projects in the Kubernetes ecosystem. I was one of the first few developers on the Helm project and a core maintainer for several years. I also helped build and maintain Draft, CNAB, and Open Service Mesh. And Service Mesh is actually the space in which I first came across WebAssembly, as it was a way to extend the functionality of Envoy proxy. If you're not familiar with Envoy, it's a core technology that a lot of service meshes build around. And as I learned more and more about what it can do and the kinds of gaps it could fill, I got more and more excited about it. And so now one of the projects that I work on is called Spin, which is a developer framework that helps people build applications with WebAssembly. Before Fermyon, I worked at Microsoft. I spent about 4.5 years there under Azure Containers. And before that, I was in the PaaS space at Deis and Engineered. The programming language I'm fighting with most these days is Rust. And there's nothing that I love more than being yelled at by the Rust compiler is drinking coffee, like iced coffee, like a huge iced coffee. I'm known for drinking coffee in like very, very large cups. I've started Big Drink Friday at my company. If you want to join, feel free. But I generally like to drink this iced coffee while also being yelled at by the Rust compiler. So the goals of today's talk is to answer, 1, what is WebAssembly? And 2, why bring it to the cloud? And 3, how do I build applications with WebAssembly? So let's jump right in. If you do a quick Google search, you'll see that WebAssembly, or WASM, is a binary instruction format for a stack-based virtual machine. Let's break that down a bit. You can think of WebAssembly essentially as a compilation target. You write your application in any one of the 30+ languages that compile to WebAssembly, so Rust, Go, C++, C#.NET, Swift, Python, etc. And when you compile your application, you get a .wasm file. And in that .wasm file, there is a set of binary instructions or bytecode targeted at a virtual machine. And you can execute that .wasm file anywhere you can execute WebAssembly. Initially, WebAssembly was created as a way to push performance forward in the browser. And what you can do with it is you can run code in multiple different languages at near native speed on the web, which is huge, right? Because now you're not constrained to using JavaScript for everything. You can do things like write some super compute intensive workload, like a game, in C or C++, and you can call that program from your JavaScript and execute your game all right within your browser. And that makes running these heavy workloads a lot more performant on the web. Examples of success stories are Adobe Photoshop, AutoCAD, and Google Earth, all which have ported their applications to WebAssembly and now successfully run them in the web. So it turns out that WebAssembly has these really great properties that make it excellent for running in the browser. And those same properties are really appealing for running applications in the cloud. Let's take a look at those as well. So number 1 is portability. Let's go back to that .wasm file. You take your application, you compile it, you get your .wasm file. That contains bytecode targeted at a virtual machine, rather than binary code targeted at a specific chip, which is what you might get if you compile a Go application, for example. This is more similar to how Java works. You take a Java program and you compile it to get Java bytecode. And then you run that on the JVM, the Java virtual machine, which knows how to run that bytecode format. So going back to the .wasm file, because it's targeted at a virtual machine, you can run that same file on ARM, AMD, Linux, Intel, and any other environment that's capable of executing WebAssembly, making WebAssembly incredibly portable. This takes us a step further than even containers, where we have to build separate images for different platforms and architectures. Number 2, WebAssembly has some really interesting security properties. The way it works is that each WebAssembly module has its own linear memory, so it can't access the host memory or memory of other modules. And it also cannot access any host API that it's not explicitly given access to. So it's deny all by default, and it can't do things like open files or access process tables or anything like that on your system. And this is the thing that actually sets it apart from all the other technologies that are similar in this space, like the JVM, CLR, and even containers, which are all not deny all by default. And we have to do work to make these things secure. So getting these kinds of security primitives out of the box is really great on the browser, but it's also really powerful to have in the cloud as well. Number 3, speed. We're always trying to make our web pages faster. So WebAssembly binaries are really small and have incredibly quick startup times. Where a container startup time is at best like half a second, a WebAssembly module can start up within the matter of microseconds, making things like scale to 0 and 0 to scale and not using compute resources when we don't really need them a reality and a really good experience. Okay, cool. That's the pitch. Now, let's play a game. This is Slats, our cat, and she is really picky about what she wants to eat. And so she's going to tell us what she wants, and we have to click the button to feed her the right thing, and we'll get points as she gets fed. So right now she wants chicken, so we're going to click chicken as many times as we can, and she really likes chicken. Oh, now veggies, and she's changing her mind to chicken now. And now she wants beef, lots of beef. Give her as much beef as she wants. She's based on a real cat, by the way. And now she wants beef. Okay, cool, chicken, more chicken, meat heavy day. All right, cool, so we fed Slats, our cat, our picky cat, about 119 times. This is Finicky Whiskers. It's a small game we designed to give a glimpse into what our vision of the future would look like. It's composed of 1 static front end, 5 WebAssembly microservices, and Redis running in a container. And so every time we clicked one of those buttons, a few different WebAssembly modules spun up, executed some business logic, and then spun back down. We fed Slats about 119 times, so over 300 modules got spun up, did what they needed to do, and spun back down. And if you go to the finickyWhiskers.com website, you can play this game if you are a cat lover and want to. It's running on a few small T2 instances on AWS, and it's powered by WebAssembly. All right, cool. So hopefully by now you're wondering, maybe, how do I build an application with WebAssembly? How do I go about doing that? And back in the day when containers came around, a lot of us, me, shoved our existing applications into a very large container image. And then we figured out, okay, well, how do I make this slimmer? How do I remove libraries and utilities I don't need? If it's really large and if there's ways to break it up, let me do that so they can scale independently and things like that. So that was really useful for getting started. We can't do that actually with WebAssembly, because by default, vanilla WebAssembly modules cannot access external resources like files, environment variables, or network connections. But there is a group of specifications that's being developed called WASI, WebAssembly System Interface, which allows non-browser WebAssembly modules to securely talk to a few select system resources. So a few of the popular things that it allows us to do on the server side is enable file system access, add environment variable support for clocks and random number generators. And that said, networking workloads are not yet possible. You can't actually compile your HTTP application to WebAssembly, you'll get an error. And even if you could, you aren't going to be able to do multi-threading. These are ongoing proposals in WASI. But we at Fermyon are a bit impatient, and we actually use this constraint to help us explore an entirely different way of building microservices. We wanted the speed and security fundamentals that WebAssembly provided, so we wanted to really make this work. And when we really thought about it, we didn't want a developer to really even deal with anything except for the business logic. So we thought, what if we could put the business logic in WebAssembly and then let the host deal with everything else, like configuring the HTTP server, for example, and TLS and whatever else. And so as we thought about this, we thought, okay, well, actually, this might be a really good experience. We let the host deal with all the hard stuff, all the tedious stuff that the developer doesn't want to deal with. The application logic lives in WebAssembly, and there needs to be something that kind of wires everything up. And that's how we came up with this idea of this project called Spin. Spin is a framework for building and running event-driven microservices with WebAssembly. It configures the execution environment for your application so you don't have to. It's a great way to get started with WebAssembly on the server, and it's written in Rust, it's open source, it's available on GitHub. This is what the CLI looks like. There's a few different commands. That first subcommand, it's called bindle. Bindle is a way you can package your WebAssembly application. You can store your bindle with your WebAssembly application plus some static assets onto a bindle registry, and then you can share and distribute and pull and things like that. Spin also allows you to build your WebAssembly components, so like this will actually like compile the application for you. Deploy is a way to deploy your services to the cloud. And new and templates are subcommands for getting started, and up is how you might test your application locally. So if you do want to get started, you can look at the templates that Spin has. Here we see there are some Go and Rust examples, HTTP applications, a Redis listener, things like that. And if you want to start from scratch, you can do that, but you can use these templates to scaffold an application for you. So here we're going to build a new application. It's going to be an HTTP application written in Rust, my new favorite programming language, and we're going to call it Hello World. And running this command will scaffold a directory with some files in it. So you see that on the right-hand side here. We have a cargo toml file, we have a spin.toml file, we'll talk about that, and we have the lib.rs file that contains our business logic. This is what the lib.rs file looks like. It contains one function. It's called Hello World. It takes an HTTP request and returns an HTTP response. And in our response, we're setting the status OK200, and we're setting the header to foo_bar, and we're setting the body to have some text, hello fermion. And on line 8, now this is the frameworky bit. We've annotated our function with a macro called HTTP component. And this macro generates a lot of glue code behind the scenes so that Spin can work correctly. You don't have to know a lot about the details. You can just know about what know that you need to have it. Because it's also an indicator for Spin. It indicates to Spin that this function is the entry point of our WebAssembly. All right, so the objective here is we're going to compile this to WebAssembly, and then we're going to run it with Spin. This is a spin.toml file. This is how you configure your application in Spin. There's some metadata up top, name, author's description. The trigger type tells Spin what kind of application this is. And so this is going to be an HTTP application. You can also set up a Redis listener. There's other kinds of things that you can do. And underneath, you'll have a list of components. We have one component. We just have one Hello World function, Hello World WebAssembly application. But if you had a set of microservices that you wanted to deploy together, you could have a list of components here. Each component has a name. This one's Hello World. And on line 10, this is like a very important piece. This is the source line. This tells Spin where on our local file system the WebAssembly module lives. So here, the path that we're seeing is target, wasm32 wasi release hello world.wasm. And underneath, line 12 is actually really important too, is the route. So this is how this component gets triggered. So when Spin starts your application, anytime someone hits the hello endpoint, the hello route, this WebAssembly component will be executed. So let's check out how that might work. First, we're going to run spin build. This is going to build the WebAssembly pieces for us. So take that Rust and give us a .wasm file. And after you do that, you can actually see that hello wasm was created. You can start and build the application in the same command, but I'm just doing the separate commands here because, just to explain like what each bit does. So here we see that the hello world wasm was created, and if I spin up, then we'll start up an HTTP server, and it'll give us the available routes, and we'll just curl that route to make sure that our application worked correctly. So here we see that our application returned status of 200 OK, header foo bar, and in the text hello fermion. You can also deploy this application to the cloud with one step, spin deploy. You will have to install the Fermion platform, which is an open source platform as a service type of piece of software that stitches together a bunch of open source components under the hood. So you can deploy that locally, or you can deploy it on AWS today. And under the hood, all of the workloads get scheduled on Nomad, which is pretty interesting, I think. OK, so going back to our cat game. As we clicked the buttons to feed the cat, Slats our cat, we were actually executing requests to spin, which was spinning up a new WebAssembly instance or a few new WebAssembly instances to handle each request. The faster we clicked, the more WebAssembly modules we started. That's why we call Finicky Whiskers the most adorable manual load generator. And this is what the spin.toml file looks like for the Finicky Whiskers application. As you can see, there's a list of components here, one for every microservice, and some metadata up top. So I hope that kind of ties everything together, and we've learned something about WebAssembly today, how we might get started. If you're interested, we'd love for you to try spin out. Listed the URL here. We're pretty active on our Discord. We like to chat. We like to hang out. And if you're new to WebAssembly or want more of the why this is useful, or even like what is a WebAssembly component, and kind of get into the specification and the details, we have some really great content on the Fermion blog that we're really active on. And if you want to reach out, my DMs are open on Twitter. Like Kelsey said, that's a dangerous thing. But I do love to chat. I'm happy to chat with anybody who has any questions or wants to geek out about WebAssembly. And the Fermion Tech handle has some really great content as well. And lastly, thank you. Just a big thank you to all the folks who made WebAssembly possible. It's like years in the making. And a lot of talks I've seen have gone into like the details of how it actually came about. I gave you like what is WebAssembly today, but there is so much that has gone into making this piece of technology. So just a big kudos to everyone who has been involved. Thank you.